this is part 2 of the previous talk, and I will skip a lot of technical details. Basically, we are interested in the mitral valve, and we all know mitral valve is harder to model than aortic valve because it's asymmetric with a larger, more floppy anterior leaflet and narrower, a little bit stiffer posterior leaflet, and it is most importantly connected with a bundle of chorded which running through the valve and is connected to the pulmonary muscles of the left ventricle. That means you can't model it without considering the motion of the left ventricle. And when the valve is damaged, you need to repair or replace the valve, and therefore you need to design a good mitral valve. But currently, all the valve design is aimed for aortic valve and is used in the reverse condition for the mitral valve, so it's not ideal. So the problem comes to us a few years ago with a group of surgery in University of Glasgow, and they designed a new bioprosthetic mitral valve. So it is designed using polyurethane material, which is tested to be bistable, and it's very durable. You can design what shape you want, and most importantly is for the first time they incorporated the chorded, which can be adjusted after the idea is after operation, and to pull a lung adjusted to make it optimized. And they are supposed to be designed with similar mechanical properties. And so they want to know or to say whether it's good enough. So what we did is to use the immersive boundary method, because we thought it was the only method which can run fast enough for this kind of simulation. But that was old version. Initially used uniform layering grid and first order approximation without bending, because the valve is modeled with fiber, and solved with the FFT, which is very fast. But limitation is you have to use periodic boundary conditions. That means you can't impose pressure driving pressure. You can only impose flow rate at the two ends. And we got a couple of papers published, and the key results is we can obtain reasonable agreement with experiments, not quantitatively in every aspect, and we can highlight the problems in the design. For example, the overstretched posterior leaflet, if you do have a chorded attached to the ventricle. And also there are a lot of modeling issues, like we predicted the opening pressure. If you give flow rate, the predicted opening pressure is always much higher than the experiments, and the valve opens, over-opening, and doesn't close at all. So we need, but also, so we want to know whether we can improve that. So we want to find out which one will help the valve to, what other effects will help valve to close. So this is a basic procedure. You got design valve, you use kind of a mesh generator and generate a final element model, and then you need to develop your own code to make it all fiber structure, because immersive boundary can only see fibers. And then you put in the IAB solver, and you use post-processing to. So this is the larger one is in anterior leaflet, and then the other one, the longer one, is posterior leaflet. And the cord is going through the valve, and then it's connected in the end to the left ventricle. So that means you cannot model this in isolation. So you need to consider the motion of the left ventricle, but we don't really want to model the heart like Charlie does. So we took a shortcut. We use MRI data and then generate the image and the motion of the left ventricle, and then use it as boundary condition for the valve. Okay, so what we do is we have a valve like this. We reverse it and put all the fibers through, and then you put a housing or disc and a guiding tube where you impose the flow rate. And then the chords are connected to the left ventricle, the pulmonary muscle group region, and then you put a left ventricle in it, or put inside the left ventricle, and then you let the motion, because all this is obtained from MRI, and the volume change is then used to generate the flow rate, which is imposed at the inlet. And then then we got some quite nice pictures of showing the clockwise vortex, which it has been observed for in vivo heart MRI and other simulations. And the interesting thing is the whole thing makes the valve even more asymmetric, because some people model half of it, but it's highly asymmetric, so you can't really just model half of it. But the disappointing result is it doesn't close still. It doesn't close at all. It still have this valve closing problem, and it's still overstretching the posterior leaflet, which is somewhere here. It's all red. It's as a stretch. And so we have to improve the model. So we moved to the second version, which Boyce just mentioned, which is the second order in time and space. And we can now add bending stiffness and also add physical boundary conditions. That means we can impose a driving pressure rather than flow rate, because that's the only way probably to close the valve, because with a zero flow rate, the valve doesn't need to close. You need a pressure drop across the valve to close it. But before that, we want to do a validation to say whether this one is good enough. So the validation we did is to validate with the classical tube, classical channel flows, where we have a lot of experience and results. And we can, basically this is a 2D channel with one section of elastic wall, and is placed in a flue box with external pressure and incoming parabolic flow rate. And then when we can compare the results with our in-house code, and when it's stable, the immerse boundary method also gives you stable, unstable results. And when it's stable, it stays the same, and the wall shape is almost overlapping with our own results, which has been extensively validated with several other codes. So we think this new immerse boundary method is really good. We could not compare it with the old version at all. So now we will look at the valve closing problem, and you see if you don't have bending stiffness in the valve still over-opens, but it closes more or less better, because now we have a driving pressure boundary conditions rather than flow rate boundary condition. And if you look at the experimental results, you will see the valve is opening, but it's not opening as much as you saw from the picture, and it's closed properly. And the chorded is bending hard to push it close as well. So we then added bending stiffness, which is not found for the structure, which is not regular. But once it's done, and the results are really nice, and you look at the closing, opening and closing is all nearly closed, and it's opened about the same angle, and that's the pressure field you're seeing, and the pressure drop is also in the right range of the experiment. Of course, in this case, with specified pressure, but if we specify flow rate, the pressure drop is in the right range. And qualitatively, you can see that the agreement with the flow rate is fairly good. This darker line is experimental flow rate with a given driving pressure, and the lighter ones is a numerical simulation of immerse boundary method. And this is really quite good, considering that we don't really have Venn-Dickson model at the downstream, and the experiment, of course, have a compliance chamber. So we really need to build a better downstream condition to damp out oscillation. And this peak here is because we are pulling the valve in the heart, and the experiment they just fix it in space. So we think if we have we can do another simulation with a fixed point, and we think we can have an even better agreement. So in conclusion, I think it's quite promising, and it is very fast, and it's very, very easy to model complicated structures. You got a fluid box, you put whatever you have in the box, and you can just start to run. So I think in future we could consider to do more complicated 3D models. Thank you.
So, other questions? Please.
Why did the valve leaflet in your computation oscillate so much as it closed?
Because we don't have Venn-Dickson model at downstream, we don't have a compliance chamber. In experiments, they have a compliance chamber attached to it. If you only impose pressure drop, the pressure drop is measured too close to the valve. There's a wave reflected, so the boundary condition we used are still not good enough, but we can do that now. We know how to do it.
Further questions? We have time. Yeah.
Why do the leaflets not close all the way? Because, in the real heart, that would generate a lot of regurgitative flow.
Yes, that's because this is as close as we can get, because this is before it opens, this is supposed to be closed because it's limited by the size of delta function. If you completely close it, you will never be able to open it because delta function is finite. If you use infinite smooth delta function, then of course you want to say something.
The valve is actually is closed as far as the fluid grid is concerned. The valve leaflets aren't actually contacting each other directly, but again, so there's this issue. You've got a finite thickness to the valve because of the regularization of the body force, or not the body force of the singular force. So the valve leaflets are actually closing. There's not any regurgitation. There are these wild oscillations because of reflected pressure waves. But there aren't. It's not regurgitating. The valve actually is closed.
Questions? If not the case,